Good morning, class. How did you enjoy the first part of chapter 6? From what I understand, it was challenging for some of you, but that's okay. I wanted to share something with you real quick before we get started about my own experience with this very material. When I was a student, I learned about these energy systems and I didn't understand them. I took tests on them, did okay, but I really didn't understand them. Then when I finished school and I got a job teaching, I had to teach these energy systems to students and I still really didn't understand them. Okay. But over the years, like literally 10 years of a yearly studying of these systems, I finally was able to understand them. Okay. So I want you all to not freak out, to not panic. Don't feel bad about yourselves or anything like that if you don't understand not only what we did in chapter 6a, but especially 6b. What we're going to do today is some complicated stuff. Okay, I'm going to do my best to make it as simple as possible. I think I'm going to have a Zoom scheduled for us all to just do like a question and answer. I'll send out announcements about when exactly that will be. But that might be a good way to allow you all to ask me some questions and maybe I can explain things in a slightly different way than I'm going to do it in this PowerPoint. Okay, so don't panic. Just try to pull some of the key concepts out of what we're talking about today. And as we go through your future, you'll build on this, right? This is sort of like your foundation, and you're going to layer more and more bricks on top of that foundation as you go, if you stay in this field, of course. All right, so let's jump into it. Do note, actually, real quick, I did add some other slides that are not from this textbook that we're using, because these are some figures and things that I really like from other textbooks that I think are a little bit easier to understand. So I'm going to have like multiple figures of the same thing. I'm going to probably talk more about one, but I wanted to have the other one there for you to look at as well in case one of them makes more sense to you or is more appealing visually. All right, so just to kind of quickly review where we were, we consume energy that initially comes from the sun and it filters down, and then we consume it by eating food, right? And the food we eat contains the 3 macronutrients: carbohydrate, protein, and fats, okay? So when we eat those things, there's some processing that has to occur before we can use those things to make ATP, right? So stage 1 kind of shows us that we have to digest the food, absorb the food, and then take those large molecules and sort of break them down into smaller molecules. Okay, so those smaller molecules are things we're going to talk a lot about today. Proteins are broken down into amino acids, which we see here. Carbohydrate is broken down into glucose, and fat is broken down into fatty acids. Okay. And those are the individual things molecules that we can send into these energy systems that we're going to talk about today, okay? Glucose has a few different forms we'll talk about. When we store glucose, we store it as what's called glycogen. All glycogen is like a big bunch of glucose molecules bound together in kind of like a clump, okay? Triglycerides are a whole bunch of fatty acids bound together, okay? But when these things enter into our energy systems, they enter as individual fatty acids or glucose. Now, just to quickly mention this, protein and the amino acids that compose protein are really not used as a fuel source very much. Less than 10% of the energy that we produce in the form of ATP comes from amino acids. Only during times of like starvation or extreme long duration exercise would your body start using more amino acids. So I'm not really going to talk about protein or amino acids contributing to fuel production today because it's pretty minimal. Primarily, the human body gets its energy from carbohydrate in the form of glucose and fat in the form of these fatty acids, okay? So these other things here I'm going to sort of save for later, but I'll just kind of throw this out real quick now and come back to it later. The last energy system we're going to talk about today is the aerobic energy system, also known as oxidative phosphorylation. Okay, I might abbreviate that as OP just because that's a mouthful to say. Before any of these molecules can enter into OP, they have to be converted into this common entry molecule, which is known as acetyl-CoA. Okay, so again, we'll come back to that later. I just wanted to kind of throw that out there now as we dive into this. Okay, so we're going to start with carbohydrate, and that's what we're going to really spend most of our time today, because if you can understand how carbohydrate gets converted into ATP, you can understand how fatty acids do as well. Okay, so just a couple quick background things about carbohydrate. Unlike protein and fat, carbohydrates' only use in the body is for energy. Okay, fat has a lot of uses. Your brain has a lot of fat in it. All your cell membranes are composed of fat. There's a lot of uses for fat. Protein, obviously, your organs, your muscles, etc., highly composed of protein. Carbohydrate, on the other hand, is just energy. Okay, that kind of speaks to an important point, that you don't need to eat a lot of carbohydrates if you're not burning a lot of energy. The more active you are, the more carbohydrate you should eat. The less active you are, the less carbohydrate you should eat, because carbohydrate is, as I mentioned, only used for energy. Okay, now these numbers here, I don't want you to worry about at all. As we'll see, though, one number that is important is that if we completely oxidize one glucose molecule, we get a gain of 36 ATP. Okay, so we'll see where all of those come from as we go down the line. Okay, this is really not a lot. Okay, if we oxidize a fatty acid, you get hundreds of ATP. So carbohydrate is a very inefficient fuel source. You don't get a lot of ATP per unit of the substrate. However, it can be oxidized very rapidly. Okay, that's why, as we'll see, when we're relying on glycolysis for fuel production, glucose is used. Okay, doesn't give us a lot of ATP, but it can give it to us fast. So when we're doing something like running a 400, which is a short duration activity, and we need ATP is supplied to us as fast as possible to allow us to run as fast as we can, we're going to rely mostly on glycolysis, which again only uses carbohydrate or glucose for an input. Okay, so again, I'm going to kind of skip this. Don't worry too much about this formula either. Don't worry about it at all, because there are more important things to talk about as we create our foundation for understanding bioenergetics today. Okay, so glycolysis is what I want to spend most of our time on. Now, I'm going to jump back really quick and show you all something. And I just referenced it a minute ago, but this is important as we sort of build on last week's information. I want you to make sure you put a star by this slide. Refer back to this slide often. Okay, these are our three energy systems: phosphocreatine, glycolysis, oxidative phosphorylation. Right, this is anaerobic energy production. This is aerobic energy production. Now, glycolysis can actually occur both anaerobically and aerobically. Now, do you know what that means? Aerobic means with oxygen. Anaerobic means without oxygen. Okay, so of course we're always breathing in oxygen, but the key is we haven't widely distributed oxygen to all of our muscles at a level that can allow them to create a lot of ATP. It takes about 2 minutes for that distribution to occur, which is why aerobic energy production doesn't take over until about 2 minutes into exercise. Okay, glycolysis is the primary provider from 30 seconds to 2 minutes. So when we're running a 400 or even an 800, something that takes us less than 2 minutes, most of our energy is going to come from glycolysis. All right, so I'm going to remember this time frame here as we move forward. All right, I'm going to jump back to where we were. Excuse me. which is here. Okay, so glycolysis can occur, as I mentioned, both aerobically and anaerobically, which means glycolysis can occur in the presence of oxygen, which would be aerobically, which is here, or in the absence of oxygen, which would be anaerobically. Okay, we tend to call this fast glycolysis or rapid glycolysis, but we call this slow glycolysis if it's aerobic. Okay, and again, the key is oxygen available. Okay, so oxygen can be available, and we can still use glycolysis. If that's the case, then the end product from glycolysis, which is pyruvate, gets converted into acetyl-CoA, which then travels on to oxidative phosphorylation. Now, if oxygen is absent, it's going to be anaerobic glycolysis or rapid glycolysis. In that case, pyruvate, which we'll see is the end product of the glycolytic cycle, gets converted to lactic acid or lactate. Okay, now, is that a problem? It can be, right? If you've ever run as fast as you can for as long as you can, you probably notice that your muscles start to burn, right? Your leg muscles, your hips, your calves, whatever. That is sort of a sign that lactic acid is being produced, and it's also starting to accumulate in your muscles. When lactic acid accumulates, we have to stop exercising, okay? It produces what we call negative feedback. And that's a problem. We can only sustain exercise anaerobically using rapid glycolysis for a short period of time. Okay, that's why you can only run all out for 60 seconds or 75 seconds, depending upon how fit you are, I guess. Okay. If we're running a little bit under our top speed, though, we're still relying on glycolysis, but there is still some oxygen that is getting to our muscles, right? So rather than pyruvate converting to lactate, if oxygen is available, pyruvate can be converted to acetyl-CoA, which again then goes on to oxidative phosphorylation, right? So again, glycolysis is going to occur one way or the other. The key is if oxygen is available, it's slow glycolysis. If oxygen is not available, it's rapid glycolysis. Presence of oxygen ultimately determines which of these two occurs. Now, usually, just to further complicate things in your mind, I'm sure both are going to occur at the same time, right? As I mentioned, I'm going to go back to this slide again. It's never just one of these contributing to ATP production. All three are always contributing. The key is how much is one or the other contributing. It's not an on or off switch. It's more like a dimmer switch, okay? So during the 3 to 15 second window, we might still get a little ATP from glycolysis and OP. Most of it is coming from here. During the 30 to 120 second window, we're still going to get a little bit of ATP from phosphocreatine and OP, but most of it is going to come from glycolysis. And again here, beyond 2 minutes, we're still going to get a little bit of ATP from PCR and glycolysis, but most of it, the vast majority of it, talking 80 to 90%, is going to come from OP, okay? So again, keep that in mind. I'm going to go back to where we were. I know what you're thinking, Professor Jet, you've been talking for 13 minutes and you've only gone through 2 slides. I know, sorry. It'll speed up as we go a little bit further. I'm trying to just kind of set some background for you before we dive into the tough stuff. So let's focus on glycolysis. And again, we're going to focus on glucose only for now because glucose is the only thing that can enter into glycolysis. So we have to burn sugar or carbohydrate in glycolysis, okay? And we see that there are essentially 2 phases of glycolysis. We have our energy investment phase, which requires us to put ATP in. So we're producing an endergonic reaction, remember that word? And then in the second phase, we have an energy generation phase where we get ATP out. So we have an exergonic phase, okay? So we produce 4 during the energy generation phase. But because we had to put in 2, our net gain is only 2, right? We paid 2, we got back 4, we really only made 2 then, okay? Now notice here, there are some other things that are produced in addition to the ATP, and that goes to what I mentioned earlier, which is the pyruvate, okay? We have this end product that is left after glycolysis. In addition to ATP, we have pyruvate. We have to do something with it, right? That takes us back to this slide. If oxygen is not available, as we see in bullet point 1, pyruvate gets converted to lactate. If oxygen is available, pyruvate gets converted to acetyl-CoA and can then travel on to participate in oxidative phosphorylation. All right, so let's take a look at, actually before we get to the cycles, one more quick thing. The sole way that carbohydrate enters into glycolysis is as glucose molecules, single glucose molecules, okay? Glycogen, remember I said glycogen is how carbohydrate is stored. It's just a whole kind of an accumulation of glucose molecules stuck together, okay? It can also enter into glycolysis as well. And it actually sort of gets to take the expressway. Okay, when we convert glucose into glucose 6-phosphate, which is just a molecule that glucose gets converted into, don't worry too much about that at all. We have to spend an ATP, but if glycogen enters directly in, we don't have to spend that ATP. So to jump back, if glucose enters, 2 are required. If glycogen directly enters, only 1 would be required, okay? So our net gain is either 2 or 3, depending the form in which carbohydrate enters. If it's glucose entering, we have a net gain of 2. If glycogen enters, we get a net gain of 3, okay? And again, that has to do with how much energy we have to put in. If we're doing glucose, we have to put in 2, we only get back 2. If we enter glycogen in, we put in 1, which means we get back 3. Okay, so let's take a look at the cycle. So notice on these 2 slides, I have the phases broken down: investment phase, generation phase. All right, so here we have 4 steps that occur, and all we're really doing is rearranging the glucose molecule, okay? And ultimately, our thing we're going to do is we're going to split this molecule in half. So the chemical formula for glucose is C6, which stands for carbon. So notice what happens here in the first phase. We're going to convert glucose into glucose 6-phosphate, right? Changing the formula from C6 to C6P. Where did this P come from? Well, that is where we have to put in an ATP. So notice that there's an ATP here. The ATP is converted to ADP. In the additional phosphate, that 3rd phosphate is taken off the ATP and added to the glucose molecule, making it C6P, okay? Glucose 6-phosphate is then converted into fructose 6-phosphate, has the same formula, okay? And then in the last step in the investment phase, we're going to take another ATP, strip off the phosphate, add that phosphate to our substrate. So now we have 2 phosphates, 1 here, 1 here. We still have the C6 that originated here. So all we've done is we've taken 2 ATPs, we've stripped off a phosphate from each, and we've added them to our glucose molecule, okay? Now, just to jump back and clarify this, if we're using glycogen automatically converts to glucose 6-phosphate. We don't have to put an ATP in. So in this case, we only have to spend 1 ATP. Over here, because it's glucose, we're investing 2, okay? All right, I'm gonna just kind of pause for a second and let you sort of assimilate. What have we done in the investment phase? We've added 2 high energy phosphates to our glucose molecule, giving us this chemical formula. Don't worry about any of these names here at all. I'm not going to ask you to memorize these. Again, what I want you to take from this is, in the energy investment phase, we're adding phosphates to our glucose molecule, okay? So then we're going to transition to the energy generation phase. Now notice what happens here. We have one arrow going down. Now at the bottom of this, we suddenly have two arrows. Well, what does that mean? Well, now that this molecule is symmetrical, meaning we have 2 phosphates and 6 carbons, we can split this molecule in half. And that's what occurs as we transition to the energy generation phase. So notice now, instead of having 2 P's and 6 C's, now we have individual single P C3, and over here, same thing. So we've taken one molecule and split it in half, and now we have 2 simultaneous reactions occurring at the same time, kind of right alongside each other, okay? So now what are we doing? Now we're gonna harvest energy, right? Up here, we invested energy. We had to put energy in. Now it's time to get the energy back. We're gonna harvest it, okay? Now, I mentioned to you in the last lecture, one way that we harvest energy is by taking electrons off of molecules, okay? Electrons cannot exist on their own. They have to be bound to these high energy carriers. That's where the oxidation reduction reaction occurs, okay? NAD is a molecule, it's a protein that is one of these electron carriers, okay? So what we see happening on this first phase here, an electron is being stripped off of our molecule, okay? So what this arrow is showing us is an electron in the hydrogen that it is attached to is being taken out of the glucose molecule, and it's gonna hang out here as NADH, okay? Now, these are just gonna exist on their own for now. We'll come back to them later, okay? Once that occurs, again, our molecule is now also gets another phosphate added to it, okay? That's where the phosphate is here, gets added back. So now we have 2 phosphates on each of the C3 molecules, okay? And then look what happens again here. Now we have an ADP that's just hanging out, and maybe that ADP came from here, right? Now we're gonna recycle it. We're gonna take that phosphate that we just added, we're going to add it to ADP, and we're going to get an ATP. And because we have 2 reactions occurring simultaneously, we now have generated 2 ATP, okay? After that happens, now again, we're left with a C3 and a single P, a C3 and a single P. Water is stripped out of the molecule here, okay? And then lastly, we have the final form of our glucose molecule still has a phosphate attached. Again, we have an ADP molecule. The phosphate is stripped off of the PEP molecule. It's added to the ADP in both reactions, again giving us another 2 ATP, okay? So what we're left with is a net gain of 2 ATP, and then the byproduct of 2 pyruvates, okay, here and here. Not to forget about also our 2 NADH, right? So if we jump back to this slide, which kind of summarizes everything, we produced 4 ATP, but we spent 2, so we have a net gain of 2. We're left with 2 NADH, which we see here, and 2 pyruvate, which we see here, okay? Now, let's think about what might happen next, okay? But first, let me summarize. So in the energy investment phase, we're adding phosphates to our glucose molecule, and then we're also going to split it in half. In the generation phase, now we're taking some phosphates back, making ATP, We've also harvested a couple of electrons, which we can also use to make energy later, right? There's a high energy potential in electrons, okay? So we've gained a few ATP, not very many, right? If we're relying on rapid or anaerobic glycolysis, we're not producing much ATP at all, right? Per glucose, we're only getting 2. And we're also going to be left with some lactic acid. So you can only sustain all-out high-intensity activity for a very short period of time because we're not getting much ATP and we're also producing lactic acid. Now, before we move on, let's just think about the enzymes. There are some what we call the rate-limiting enzymes for glycolysis. And the major one is, this is a fun word, phosphofructokinase. Okay, the abbreviation for that is PFK. Phosphofructokinase will be sensitive to different things. The more phosphofructokinase is stimulated, the faster glycolysis goes, and the less it's stimulated, the slower glycolysis goes. Okay. ADP levels rising stimulates PFK. Okay. If oxygen is abundant, PFK is inhibited, and that would act to slow glycolysis down. All right. We'll come back and talk about the rate-limiting enzymes shortly as well. Okay. So as I mentioned, if oxygen is not available and glycolysis is proceeding anaerobically or in a fast way in the absence of oxygen, pyruvate is going to actually combine with the NADH to form lactic acid, right? So NAD can only hold on to that hydrogen for a short period of time, okay? If oxygen is available, the NADH can go to the electron transport chain. If oxygen is not available, the NADH is like, hey, I can't hold on to this hydrogen. You got to take it back, right? So what it does is the hydrogen is released and it combines with pyruvate to form lactate or lactic acid. So notice that pyruvate here has some open spots, but once it interacts with NADH, now the hydrogen, these open spots are filled with hydrogens, and that turns pyruvate into lactic acid, okay? We're not going to focus too much on that. I just want you to kind of know what the result is if oxygen is not available. Okay, if lactic acid accumulates in your muscles burn, you have to stop exercising, to put it very simply. Okay, so let's say oxygen is available. Okay. If oxygen is available, then the oxidative phosphorylation system is running. It's working, okay? And it wants substrates, okay? Pyruvate is a substrate that can go there, as is NADH, okay? So it kind of shows us here that these things can be combined ultimately to be converted to acetyl-CoA, and also provide some NADH, which we can use later to produce ATP in the electron transport chain, okay? So let me just jump ahead really fast. So oxidative phosphorylation has 2 cycles. It has the citric acid cycle, which you see written here. The citric acid cycle is also called the Krebs cycle. They're both referring to the same thing, okay? I might refer to them either way, so just kind of get used to that, okay? Then the other phase is known as the electron transport chain, which we abbreviate and call it the ETC. So Krebs cycle always occurs first, ETC is second. Now, before anything can enter the Krebs cycle, as we mentioned, the substrate has to be converted to this common entry molecule, which we call acetyl-CoA. Okay, so pyruvic acid, if oxygen is available, it can be converted into acetyl-CoA. It can then enter into the Krebs cycle. Amino acids, should we be in starvation state, We can use amino acids to produce ATP, but they also would first get converted into acetyl-CoA. Fatty acids, same thing. Triglyceride, again, is a bunch of fatty acids mushed together. They would be split apart, and then individual fatty acids would be converted to acetyl-CoA, where they would enter the Krebs cycle. So here are a couple different pictures of the Krebs cycle. This is the one from our textbook, which really just kind of simply shows what's happening. So in the critical thinking assignment, I asked you to sort of summarize what the Krebs cycle does. This slide actually shows it very well. The whole purpose of the Krebs cycle is to, or the citric acid cycle, again, remember they mean the same thing, harvest electrons. So at every step, almost every step in this cycle, electrons are being stripped out of this acetyl-CoA molecule. Those electrons are then sent to the electron transport chain where, as you see here, a whole lot of ATP is going to be produced, right? These electrons, the energy that is bound in these electrons is used to resynthesize ATP by binding ADP and inorganic phosphate together. So inorganic phosphate is like unenergized phosphate. The electrons energize it and they make it organic, and then those three organic phosphates join together to give us ATP, okay? So this slide shows us the citric acid cycle, and this is the one I love. This is probably, obviously, again, I don't want you all to focus on any of these names. I'm going to talk about a few of them, but just block them out of your memory for right now, okay? I'm not going to ask you to memorize these. I'm just going to point out a couple key things here. Okay, first, again, we have our three macronutrients, pyruvate representing carbohydrate. All three would be converted to acetyl-CoA first. Once they do that, they then enter into this cycle, okay? So notice here in the plain text, these are enzymes. Any word that ends in "ase" is an enzyme. Oops, sorry. Notice that some of these enzymes have an interesting second word, and that second word is dehydrogenase. Okay, so that word should tell you what the enzyme does. Dehydrogenate means remove the hydrogen. Okay, so wherever we see a dehydrogenase enzyme, which this is the first one, this is the most important one, isocitrate dehydrogenase. This enzyme removes a hydrogen from isocitrate, giving us an NADH molecule, okay? Same thing occurs here. Ketoglutarate dehydrogenase removes a hydrogen from the ketoglutarate molecule. Down here, succinate dehydrogenase removes a hydrogen from succinate. Now, FADH, NADH, basically the same thing. The only difference is we get a little bit more ATP from one. Don't worry too much about that now either. Just kind of know they do the same thing. And then lastly, we have malate dehydrogenase. Again, removes the hydrogen from the malate molecule, okay? So what we've done, as acetyl-CoA enters, we have removed essentially 4 hydrogens from each acetyl-CoA, okay? Giving us this number that we see here. 3 NADHs, 1 FADH. Now, for every molecule of pyruvate, we get 2 acetyl-CoAs. So this is going to occur twice. Once, twice. Okay? 1 pyruvate produces 2 turns of the citric acid cycle. Now, we do have at the very bottom, we do actually directly produce 1 ATP per turn of the Krebs cycle here, okay, which will contribute to our total later. But the major purpose of this, and again, I asked you this in the critical thinking assignment, how can we simply describe what the major purpose of the Krebs cycle is? The Krebs cycle's major purpose is to harvest electrons from the acetyl-CoA molecule and then send those electrons to the electron transport chain, okay? One last thing to mention here, the rate limiting enzyme of this cycle is this first dehydrogenase, this isocitrate dehydrogenase. When oxygen is available, this enzyme is stimulated to increase its activity. When oxygen is not available, this enzyme is inhibited and decreases the rate of this cycle. Okay? ADP is a stimulator for this enzyme as well. ATP is an inhibitor, which why is that? Well, if ATP is available, why would we need to make more, right? So that's kind of how that works. And now again, this is another picture from our textbook. I'm not going to go through it. I think this just kind of shows you another way to look at this. So if this picture is more appealing to you, you can kind of look at it through the lens of what I just talked about, but it shows exactly the same thing. Okay. Don't look at this box yet because I don't want this to confuse you. I have a better box that we'll look at that summarizes how much ATP we're going to get out of this. So what we're looking at from one glucose molecule that goes through both glycolysis and oxidative phosphorylation is a net gain of 32 ATP. Okay, we get 34, but we have to spin 2, so we're looking at 32 total. Okay. Now that would occur if oxygen is available. So we would do aerobic or slow glycolysis, meaning the glucose molecule goes through glycolysis, leaving us with pyruvate. If oxygen is available, then that pyruvate gets converted to acetyl-CoA and enters into the Krebs cycle in electron transport chain. If that occurs, this is the number of ATP that we get, 32. And that is shown, let's see if I can move this window. Here we go. Here, okay. Where does it all come from? From glycolysis, we get 2, okay? And then from the NADH that we produced in glycolysis, we get another 5, okay? You get 2.5 per NADH, so 2 times 2.5 gives us 5. We get another 5 from converting pyruvate to acetyl-CoA, okay? We saw that we directly produced 2 ATP during the Krebs cycle, which was, where was it? Here, okay? 1 per turn. We always have 2 turns, giving us 2. And from all of these NADH and FADH that we harvest, once those go to the electron transport chain, we get 15 from the NADH, 3 from the FADH. This total gives us 32, okay? So from one molecule of glucose, if that molecule goes through glycolysis and oxidative phosphorylation, we get 32 ATP. And this is another breakdown. This is a chart that I pulled from another textbook. I kind of like this one a little bit better. But this basically matches, what we saw here. So I'm not going to explain it to you all again. How am I looking on time? Let's see, 38 minutes. So again, I want to point out this is aerobic glycolysis and oxidative phosphorylation. If we're doing anaerobic glycolysis, the pyruvate does not get converted to acetyl-CoA, so none of this here would occur, right? Instead of sending pyruvate to OP, it becomes lactic acid, and we have to stop exercising a lot faster. Now, we focused on glucose. We haven't talked about fat much, mainly because there's no difference, okay? As we saw way back here, all 3 of the macronutrients, before they can enter the Krebs cycle, they get converted to acetyl-CoA. So fatty acids are going to be metabolized the same exact way as glucose because they both get converted to acetyl-CoA. The key is how many acetyl-CoA do we produce per fatty acid, right? That's a big difference. Let's jump back here. So if we're going to use fat for fuel, which we would do during aerobic exercise exclusively, okay? The conversion process from fatty acids to acetyl-CoA basically sees us take the fatty acid, which is a long string of carbon molecules. We chop those carbon molecules up into a series of 2 carbon fragments, okay? Acetyl-CoA is a 2 carbon molecule. So we might have a fatty acid that has 18 carbons. If we had an 18 carbon fatty acid, we could chop that up into 9 acetyl-CoA, right? So where we told you before, glucose results in 2 turns of the Krebs cycle, okay? A fatty acid might result in 9 turns of the Krebs cycle, which would result in a lot more ATP, okay? So we get more ATP from fat, not because the cycle is different, but because we provide more acetyl-CoA. Okay, so that's the key difference there. So that process of converting fatty acids to acetyl-CoA, it has a name. Again, don't worry too much about this. I just wanted to show it to you. That process is called beta oxidation. Beta oxidation is the process of taking fatty acids and converting them into a bunch of acetyl-CoA molecules. Once that process is done, this occurs exactly as it did with glucose, right? So it's the same. And that's the beauty of this too. And that's one thing it took me a while to figure out as a student. I'm like, well, crap. I was always thinking that fat metabolism was confusing, but it's actually exactly the same as carbohydrate metabolism in terms of oxidative phosphorylation. So this is just, a slide. This is one I pulled from another textbook. I like this one because it shows that this occurs inside the mitochondria, right? Oxidative phosphorylation occurs inside the mitochondria. Glycolysis occurs in the cytosol of the cell, but beta oxidation would occur inside the mitochondria. This, again, is similar to a slide that I showed you earlier that shows all 3 of our macronutrients must be converted to acetyl-CoA before the end of the Krebs cycle, okay? So that's it. That's the summary, right? Let me just back up and say one more thing. So from a glucose entering, we get 32 ATP. Sounds like a lot, but it's not really very many. If we sent a fatty acid, there's a common fatty acid known as a palmitic acid, okay? It has 18 carbons in it. So if we took that palmitic acid, as we convert it to acetyl-CoA, we would produce 9 acetyl-CoA, right? So the number of ATP we're going to get from one fatty acid is going to be over 100 because we produced so many more acetyl-CoA compared to what we did with glucose, right? From glucose, we only get 2 acetyl-CoA, ultimately allowing us to produce 32 ATP. From a fatty acid, we might get 9 acetyl-CoA, which would bump this number up greatly, right? Different fatty acids have different numbers of carbons, so I'm not going to throw out specific ones to you other than the one that I just did. And I don't even want you to remember that. The key thing I want you to remember is fatty acids have a lot of carbons, where glucose only had 6, okay? So we get more ATP from fat because there's more carbon in fat, allowing us to make more acetyl-CoA, which ultimately means this cycle is gonna go round and round and round many, many more times, okay? And in the, I feel like I left out a picture that I really wanted to show you all. I'll have to jump back here and show you. In the electron transport chain, again, I didn't specifically focus on this very much. This also occurs inside the mitochondria, as we see here. This is the second phase of OP. And here, all of those NADHs that we produced, that we saw here, right here, 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 and here, they all then go to the electron transport chain. Sorry, I'm going back and forth a lot, I apologize. In the electron transport chain, the electrons are pulled off of the hydrogen and they are used to reformulate an ATP molecule, right? So these two electrons, the energy contained in those electrons is used to sort of re-energize this inorganic phosphate and join PI and ADP back together to produce ATP. So the vast majority of the ATP that comes from oxidative phosphorylation comes from the electron transport chain. So if I asked you to summarize, again, in a different way, what occurs in the Krebs cycle, we're harvesting potential energy, and then in the electron transport chain, we're using that potential energy that we harvested in the Krebs cycle to produce ATP directly, okay? So that is the end. I hope I kept that as simple as possible. There's a few summary points you can check out here, some sources. As far as our tasks go, we have the study questions and the critical thinking assignment. I want you all to be aware that we do have an exam that's coming up in a couple weeks. What I'll do is I'll open up the exam on Wednesday the 7th, and you'll have a couple days to do it on your own time. It just needs to be done by Friday the 9th at 8 p.m. Assignments are due end of the day. I want the exam done by 8 p.m. just in case you have any questions, you need to contact me, okay? I will also make an announcement here shortly, maybe like Monday, about hosting a group Zoom chat. We'll probably aim to do those on Fridays, like in the morning, to give you time to ask questions about the assignments before you submit them, okay? So be on the lookout for that. It's voluntary. If you want to pop in and ask a question or just listen or whatever, that's totally fine, but I'll try to set those up, okay? So again, don't panic. If you didn't understand this, it's normal, okay? The next time you study it, it'll make a little bit more sense, and you'll just continue to layer information on top of information, and eventually in 10 years, you'll be like, I understand it now, okay? Hope you all are enjoying this class so far, and I will talk to you soon.